All right, so here looking at the derivatives of trigonometric functions, and right off the bat, here are the derivatives of the 3 primary and 3 reciprocal trigonometric functions, by far the most important being the top 3. And so the derivative of sine is cosine, that's quite pleasant. The derivative of cosine is negative sine, and the derivative of tangent is secant squared x. Now, before I talk more about that, really, once we can prove just, for example, just that the derivative of sine is cosine, or once we can prove that the derivative of cosine is sine, because those two are so similar, once you prove one of those, it's pretty easy to prove the other. And once you know that those two are true, that we can just use the quotient rule or product rule or some sort of rule like that to differentiate all the rest. Remember, tangent we can think of as sine divided by cos. And so once we know the derivatives of sine and cos, we can know all the rest. So the derivatives of the reciprocal functions are less important. I don't expect you to memorize those, but we should memorize the derivatives of the 3 primary trigonometric functions. Clearly they're important functions. We should know their derivatives. Keep in mind, everything you see here is only true if it's in radians. If we're thinking in degrees, these derivatives are not quite as simple. And so everything we're talking about is in radians. And otherwise, these derivatives are not as simple. Like I said, radians are much more pleasant to work with when working with calculus. And one of the problems we'll look at in our notes is we will prove algebraically that the derivative of cosine is minus sine. And the derivative of sine is cosine. It can be followed in a similar way. That's it. Let's just use these first. So let's let f of x be x times the cos of x plus 2 tan x. Okay, let's find the derivative. Well, first of all, one thing that's easy to miss is that we have to use the product rule here. Because notice we have a linear function multiplied by a trigonometric function. And so just to differentiate that first part, we need to use the product rule. So the derivative, we'll start off with the derivative of x, which is 1 times the cosine of x, plus the other way around, x times the derivative of cos x, which is minus sine x we just saw. And it's really easy to miss these things. In fact, we'll see this a lot going forward, so it's really easy to miss for example, that we have to use the product rule at times. Anytime you're multiplying one thing that's not a constant, so therefore one function by another, you have to use the product rule. It's really easy to miss that. That's the second term, 2 tan x. 2 is a constant, so I can just focus on the derivative of tangent and multiply that by 2. And so the derivative of tangent is secant squared, and so plus 2 times secant squared x. All right, at this point, I'm pretty much done. I might as well just clean it up a little bit. I'll write it as cos x minus x sine x plus 2 secant squared x. Now remember, all trigonometric functions are related to one another through various identities, so there's never one way of writing a trigonometric expression. There's quite often there's one simplest way, but I'm fine with this. That's it. There's always more than one way. For example, 2 secant squared x we could write as 2 over cos squared x. And for writing as 2 over cos squared x, we could find a common denominator for everything. And I don't really care about that right now, as long as you understand there are those options. And so with that said, though, I just need to work through a few examples here. So let y equals sine t over 1 plus tan of t. Find dy dt, find the derivative with respect to t. So probably not surprising here, we have to use the quotient rule. And so the quotient rule, let's see, dy dx. First, I want to find the derivative of the numerator. The derivative of sine t is cos t times the denominator left alone, 1 plus tan t. Those brackets are really important. It's a binomial. Minus the other way around, the numerator as is, times the derivative of the denominator. The derivative of the denominator, the derivative of 1 is just 0. The derivative of tan t is secant squared t. And all this is divided by the denominator squared. And keep in mind, this term right here does not have a factor of 1 plus tan t. Otherwise, we should definitely cancel it out from everything. But I'll just leave it like that. If I need to simplify it, well, I can simplify it, but sometimes things just don't get terribly simple. So all I really want to do now is really at this point you just mostly need practice with these things. But I do want to prove algebraically that the derivative of cosine is minus sine. And I'm picking that one because it's essentially the same idea as proving the derivatives of sine is cosine. So let's prove it. And I can prove it algebraically using a few things. First, I need to go back to two derivatives that we've seen before, especially this one. The limit as x approaches 0 of sine x over x is 1. That was proven using the squeeze theorem earlier on. But more important than the proof is just that knowing that's true. And this limit right here is going to come into play somewhere. That's less important, but it has come up, I think, just once in a previous lesson. Either way, the limit as x approaches 0 of cos x minus 1 over x is 0. Okay, using that and the definition of the derivative, I can prove that the derivative of cos x is minus sine x. So how do we do this? Well, let's start by saying d dx of cos x will equal the definition of the derivative. We'll start with cos of x plus h minus cos of x all over h. And actually, I should say the limit as h approaches 0. So let me squish that in there. Take 2. All right, so that's just the definition of the derivative with, instead of f, I have cos x. Okay, so now keep in mind, if I look right here, actually I'll change my color up a bit. I'll get to those later. If I look right there, remember cosine is a function. It's not a number or a variable. I can't distribute cosine, but I can use the sum identity for cosine. So the cos of x plus h is the same as the cos of x times the cos of h minus the other way around. The cos of x times the cos, so the cos of h times the cos of x. Sorry, that's not what the identity is. Helps if I can remember it properly. It's cos x times cos h minus sine x times sine x times sine h. And that is the sum identity for cosine. And there's various identities that you learned about in pre-calc 12. But the sum identities for sine and cosine are two of the more important ones. That's it. Let me just write minus cos x over here. And remember, as always, when we're working with a limit like this, our goal, since our limit is h approaches 0, is at some point we want to find an equivalent expression so that we're not dividing by, we can evaluate the limit without dividing by 0 at any point. All right, what can I do next? Well, remember I said at some point these limits up here come into play. That can maybe be a little bit more obvious if I just switch the order of these two terms around. Okay, I just switch those two terms around. Now, if I do that, if I look at these two terms here, I can take a common factor of cos x out. And why is that helpful? Because I will get I'll start to see the form of one of those limits up there. So take a factor of cos x out. I have cos h minus 1 right here, minus sine x times sine h all over h. Well, right here, cos h minus 1 over h, that is the exact same form as what I see up here. Yeah, that's an x. It doesn't really matter. As long as the variable that's in there is approaching 0, we know that limit's going to equal 0. So now that said, I still have other stuff going on around there, but I can get at that if I now just kind of break this up into two fractions as cos x times cos h minus 1 over h, and then minus over here sine x times sine h over h. And now notice I can see my other limit right here. Sine h over h as h approaches 0, sine x over x as x approaches 0. The only difference is the variable is different, but it's the same idea. And so if I do that, maybe what I'll do is to make it a little more obvious, I'm going to rewrite this term right here. Instead of sine x times sine h over h, I'm going to write it as sine x times sine h over h. I'll write it like this. It's the same thing, but it makes it more obvious how this expression is going back to those two limits. So at this point, I can actually evaluate my limit now. I can actually evaluate the limit as h approaches 0. Because yes, h is approaching 0, so I can't just substitute that h there with 0, but I do know that everything you see highlighted in blue, I know that all of that as h approaches 0 equals 0. And I know that all of this, as h approaches 0, is 1. So I can evaluate my limit. And again, the cos x and the sin x don't really matter. That's not an h, they're an x. So they just are, you can think of the x as being like a constant. And so what's left here? I have cos of x times 0. Okay, clearly that cos x is going to be gone. Minus the sine of x times 1. And so I can see this equals minus sine x. And remember, all this is the derivative of cosine. So now I can bring that down here, and I've proven that the derivative of cosine is minus sine x. And so what did it require? It required these two limits, okay, one of which was extremely important, that sine x over x equals 1, and it required, using the definition of the derivative and some identities. As always, though, when I prove some sort of derivative, when I prove anything in this course, please don't waste any time trying to memorize it. Like, I'm never going to ask you just to regurgitate a limit or a proof to me. But it's also good to know that we are at a level now where we can actually prove a lot of these things. We don't have to just, take it as some sort of commandment that some person figured out a long time ago that we can't figure out. We're at a level now where we can actually algebraically figure out and understand and see where a lot of these things come from. With that said, the most important part right now is working with these derivatives, and you will all the time now find that you're combining it with the product and quotient rule. And soon we'll start combining it with something called the chain rule as well, but not quite yet. So that's where I'm going to stop.